Okay, students, welcome to Friday Happy Math Hour. Today, I am going to start the the NCBM 0324 at Math 1324. And from now on, it's going to be like this. It's going to be separated. Okay, Ms. Chuka and Mr. Ruben, they're going to be doing the 1314 and the NCBN 0314, and I'll be doing the 0324 and also the 1324. This week's lesson is writing exponential equations into logarithmic form. Okay, so let's start. Okay, today we're going to cover exponents, radicals, and logarithms. I believe exponents and radicals, they already were explained on the 0324 this week. And also for the 1324, we started on exponential functions, how to evaluate them and how to graph them. So in this session, I will be covering those topics. So here, topics covered are exponent properties, converting radical expressions to exponential expressions and vice versa, simplifying radicals, exponential functions, graphs, writing exponential equations into logarithmic equations and vice versa, and also graphing logarithmic functions. Okay, for the exponents, to apply the properties, there are certain rules that you gotta know. Okay, and I'm going to list the rules here by the definition and also what you do in order to simplify them. So for example, this is rule number 1. It's called the product rule. If you have a to the m times a to the n equals to a to the n plus n. In other words, when you have the same base, here, this is called a base, which I'm going to explain to you in the next slide, you add the exponents, okay? Rule number 2, this is called the quotient rule. If you have a to the power of n divided by a to the power of n, then you subtract the exponents. It's going to be a to the n minus n. And a cannot equal to 0 because if a is 0, it'll be undefined. This is called the power rule. If you have a to the power of m, right, raised to another power, then we multiply the power. So it's going to be a to the n times n. This is called the power of product rules. Here is a combination of rule 1 and rule 3, right? So if you have a times b to the n power, then it's going to be a to the n times b to the n. Furthermore, if you have say for example here, guys, the power of a and b is 1, right? But it's not there, but we know it's 1. That's why it's going to be a to the n times b to the n. But here is when a is another number, like another another integer. Okay, so for example, if you have a to the m times b to the n raised to the p power, then it's going to be a to the m times p and b to the n times p. So in other words, you multiply the power of p times m and the power of p times n for both a and b. This is called the power of quotient rule. If you have a parentheses a divided by b to raised to the nth power, then again it's going to be a to the n divided by b to the n. And b cannot be 0 because if b is equal to 0, then this expression is undefined. And also, same thing as rule number 4, right? For example, this one here. If you have a to the m divided by b to the n raised to the p power, it's going to be a to the m times p divided by b to the n times p. If this seems confusing to some of you students at the moment, I will clarify this with doing examples of each one of the rules until you guys feel satisfied that you understand the material. So for now, I'm just reading the rules. This is rule number 6, which is called the negative exponent rule. If you have a to the negative exponent of n equals 1 over a to the n, it becomes positive, right? But it goes as a denominator. And a cannot be 0 because if a is 0, again, as before, it will be undefined. And furthermore, this will make more sense here, guys. If you have a fraction raised to a negative exponent, all you do is do the reciprocal and it becomes positive. In reality, that's what we're doing here. Okay, but this is more this is more visual. Okay, but these two rules are the same. This is called the zero exponent. The zero exponent rule. If you have a to the zero power equals 1. So anything to a zero power, guys, is going to be 1. Okay, and a cannot be 0. And this is a fraction exponent, right? This is my exponent, the fraction. So you have to convert it into a radical. So a to the power of m divided by n is going to be the nth root of a to the n power. These two are the same. Okay, but this is easier to evaluate without using a calculator. This one here, and I'm going to show you on the next slide, I believe. Okay, so these are the rules that you guys must be aware of. And n has to be more than or equal to 2, because if not, it'll just be a to the power. I mean, it'll just be a, because if it's a to the first power, right? I mean there's a thing as I mean the index being to the first power, it always has to be a squared or more. So that way it has to be 2 or more. Okay, now here are examples of the product rule. If you guys have any questions, guys, as I go along, please raise your hand up or else put it in the chat, because I have I have 2 computers. One that I'm doing the PowerPoint, and then I have another one that I see the comments, and also when students raise your hand up, so I can see if you guys have any questions. So please feel free to ask any questions or just stop me as I'm going by. So this is rule number 1, right? The product rule. If you have a to the m times a to the n equals to a to the n plus n. What does that mean? A is the base, right? The a is the base and the m is the exponent. Now, must have the same base to apply the rule. This is what I meant earlier. These 2 bases must be the same in order for you to apply the rule. If they're not the same base, you cannot apply the rule. Okay. Example. Let me go back. Previous one. Okay, here. Example 1. If you have x cubed times x squared, this is like a long way, so you guys can understand what's taking place. If you have x cubed times x squared, if you notice the x cubed is in blue, because x cubed is the same thing as x times x times x, right, in blue here. And then x squared is in green, right? So times x squared is going to be, the green is x times x, right? The x squared. So x times x times x times x times x 5 times is equal to x to the 5th power, right? But you're not going to do it this way, right? Because instead you're going to apply the rule. By the product rule, you see we have x to the 3rd times x to the squared is equal to x to the 3 plus 2, which equals x to the 5th power. In other words, you can go from here, from x cubed times x squared, all the way to the answer. Because you can do this actually in your head if you know the rule. Okay, now this is rule number 2. This is example number 2. X to the 7th times x to the 3rd. Can somebody tell me what the answer is? Just put it in the chat. Anybody?
Yes.
Yes, Daphne. I think we lost her. Okay, but anyway, guys, let me give you guys a hint here. You see, they have the same base, right? So they have the same base. We can apply the rule. So it's going to be x to the 7 plus 3, which equals to x to the 10th power. And again, we can go from here, from x to the 7th times x cubed, all the way to the answer, right? Because we can actually do this in our heads. We can add 7 plus 3, which will be x to the 10th power. Example 3. We have x squared times y to the 4th. If you notice, they're not the same base. So the rule cannot be applied. So your response, it stays how it is. So it'll be x squared times y to the 4th, because these 2 cannot be combined. So this is your answer. Okay. Now they're going to get a little bit more challenging. Okay, but they're not as hard as it seems. So for example, if you have parentheses 5x to the 4th, close parentheses, times open parentheses, negative 3x squared, close parentheses, right? So we're gonna multiply the coefficients. These numbers in front are called the coefficients. So we're gonna multiply 5 times -3, right? We're gonna I'm gonna stick them together, and then times, right? The x's have the same base, so we're gonna apply the rule on the variables, which are the x's. So 5 times -3 will give us -15, and 4 plus 2 is equal to 6. So we have -15 x to the 6th power. And again, you can go from the example at the beginning all the way to the answer by multiplying 5 times -3 is -15, and if you have the same base, right, what they do here, so we add the exponents, it's going to give us -15 x to the 6th power. Example number 5. Here, if you notice, we have -2 times -3, right? And then we have we have x to the 4th times x to the 5th, right? So we're going to combine the x's by adding the exponents. We have y cubed times y squared. Also, we're going to combine the y's, right, by adding the exponents. So this will give us +6 x to the 9th, y to the 5th power. So this is my result. Example number 6. We have parentheses -5x y cubed, close parentheses, times, for open parentheses, 6x cubed. Okay. So again, we're going to multiply the -5 times 6, which will give us -30. Right? And then we have x times x cubed, same base for the x's. So we're going to add the 1 plus 3 is equal to 4. And the y just stays how it is, because on this one, on the 6x cubed, there's no y there. So we just bring the y over. So this is my result, -30 x to the 4th y cubed. This is the last one here. So 3 times 8 is 24, right? They both have an x to the 4th and x to the 5th. So we're going to add the x's, so it'll be x to the 9th. We have y cubed times y, so we're going to add the exponent of the y's. So it's going to be 4. So this is my result, 24 x to the 9th, y to the 4th. Now let's move on to the quotient rule. Okay. So the quotient rule, if you have a to the m divided by a to the n, right? We subtract the exponents. It's going to be a, which is a base, n minus n. Example: we have x to the 5th and x squared. Right, same base. So we apply the rule. So it's going to be x to the 5 minus 2. So it's going to equal x to the 3rd power. Let's do example number 9. We have x to the 10th divided by x to the 7th. And again, they have the same base. So we subtract 10 minus 7, which will be 3. That's why here, guys, I went straight to the answer. Because once you know the rules, you can do this in your head, right? So it's going to be 10 minus 7 will be 3. So it's going to give us x to the 3rd power. Number 10, we have x to the 4th divided by x to the 8th, right? We know they have the same base. So it's going to be x to the -4. Why -4? Because 4 minus 8 is equal to -4. And later on, we're going to be applying the negative exponents, right? Which will be rule number 6. But for now, we leave that as the answer for now. Okay? Now comes rule number 3, which is a power rule. Here you have a base a to the power of m raised to another power of n. And the rule is you're going to multiply the power. So it's going to be a to the m times n. Okay, so example. Right, we have x cubed raised to the 2nd power. So we're going to multiply the exponents, right? So it's going to be, well, this is relative. You can do it like another way, okay? But I mean, without using the rule. But it's better to use a rule because you get the answer quicker. For example, x cubed squared is the same thing as x cubed times x cubed. Then if you want, you can apply rule number 1, which is a product rule, right? Then you add the exponents. Or you can even expand it more. This will be x cubed will be 1, 2, 3, right? That's the first x cubed, and this is my second x cubed, which will give us x to the 6th power. But if you apply the rule, right, which is easier, you multiply the exponents, so it'll be x to the 3 times 2 is going to give us x to the 6th power, right? So we can go from the problem, from the example, all the way to the answer, right? That's what I did here. I just show you this, this step. But I believe from now on, I'm going to go straight to the solution. So for example, this one here, we have negative x to the fourth power squared. Okay, so this is going to give us x to the eighth. Okay, you'll be thinking, how is x to the eighth if it's negative? Okay, so let me break it down for you guys. If you have a negative raised to the, raised over here at the end to the even power, it's always going to be positive. And here's the reason why. Negative x to the fourth squared is the same thing as negative x to the fourth times negative x to the fourth. Right? Two negatives, when you multiply them, right, becomes positive. That's why it's going to be x to the eighth power. How about this one here? Notice the negative y squared raised to the third power, right? Negative. So here, guys, if this exponent is odd, and you have a negative base, it's going to be odd. The answer is going to be negative. But here's how the answer takes place. It's going to be negative y to the sixth power. Here's the reason why. Okay, how? Okay. This negative y squared, right? Because everything's in parentheses, it means negative y squared times negative y squared, right? Negative y squared times negative y squared will give you positive y to the fourth. Then you multiply it again times negative y squared, right? Because it's cubed. So negative y to the fourth times negative y squared is going to give us negative y to the sixth. Okay. If this kind of confuses you guys, break it down like I did here. Okay, and then take it slowly, and then so that way you can make sure that you answer the answer correctly with a positive or negative sign. But here's the observation: if the base raised to a power, right, and is raised to a second power here, if this is even, the answer will always be positive. If it's odd, right, and this is negative and it's odd, like the 3 there, the answer is going to be negative. That's just like an observation. Okay, now the power of product rule and power of quotient rule. Rule number 4. If you have a power of a product rule, right, if you have a times b to the n equals to a to the n times b to the n. Example. Right, so by applying the rule here, the rule number 4 is going to give us x squared times y squared. This will give us 2 cubed, right? 2 cubed times x cubed. And 2 cubed can be simplified further. 2 cubed is the same thing as 2 times 2 times 2, which will give us 8. So it's going to be 8x cubed. Okay. So here's where we apply the rule. Remember the rule, guys, that we had like a to the m times b to the n raised to the p power. When I was explaining those rules, here's where you apply it. So this is going to give us x to the 3 times 2 and y to the 4 times 2. So 3 times 2 is 6 for the base of x, and 4 times 2 is 8 for the base of y. Okay. Again, remember this, guys, right? We have a negative coefficient here, and it's odd, so the answer is going to be negative. Remember that? I'll show you the observation. So negative 3 to the third power will give us negative 27. And x squared to the third power will give us x to the sixth power. And y raised to the third power will just give us y to the third power. But this is how we do it. How? Okay. So again, you can break it. Right? So negative x squared y to the third power is going to be parentheses negative 3x squared y times negative 3x squared y times negative 3x squared y. Right, negative 3 times negative 3 times negative 3 will give us negative 27. And x squared times x squared times x squared will give us x to the 6. And y times y times y will give us y cubed. But like I said, you can go from the example, from the original problem, all the way to the answer if you know how to apply the rules. Or, here's another way. By applying the rules, right, it's going to be negative 3 to the 1 times 3, because there's like a 1 there. Times x to the 2 times 3 and y to the 1 times 3, because there's no exponent, there's like a 1 there, okay? That will give us negative 27. Those give us x to the 6, and the y to the power of 1 times 3 will give us y to the third power. That's my answer. there's different ways to get the answer, guys. Just like I tell my students, in math, there's always different ways. But most of the time, there's only one solution, unless it's infinite solutions or no solutions. But in math, there's always one answer. Okay, unless it's infinite or no solution. Now comes the power of a quotient rule. Again, this is similar to rule number 4, right? But now instead of the product, it's going to be the quotient. Example, parentheses x divided by y to the third power is going to give us x cubed, y cubed by applying the rule. We have x. Let me go back. Let me go back real quick. We have x squared divided by w to the third power, right? These are not the same bases, right? That way we can distribute. It's going to be x to the 2 times 5 and w to the 3 times 5, which will give us x to the 2 times 5, w to the 3 times 5, which will give us x to the 10 divided by w to the 15th power. And this cannot be simplified, right? Because these are not the same base. We have an x, we have a w. That's why that's my result. Okay. Now comes the negative exponent rule and the zero exponent rule. So this is rule number 6, the negative exponent rule. If you have a to the negative n, right, is equal to 1 over a to the nth power, and this becomes positive, the exponent. And like I mentioned earlier, a cannot be 0 because if a is 0, it's undefined. So let's do examples here. This will give us x to the negative 5th power is going to be 1 over x to the 5th power, right, by applying the rule. 3 to a negative 2nd power is going to give us 1 over 3 squared, right, by applying the rule, but 3 squared can be simplified to 1 over 9. This is my final result, 1 over 9. If we have parentheses x divided by y, close parentheses to a negative 3rd power, right? Remember what I said, guys? You use a reciprocal and make it positive. But this is so this is my answer: y cubed divided by x cubed. But how? Let me show you how. Let me show you why this is equal to this. This will be equal to this. Okay, this is the reason why. Right? Remember, for the rule for a negative exponent, we put it over 1, right? Under then it'll be xy to the positive 3rd power. If we have 1 divided by a rational number or expression, right? This becomes times, and this one here you flip it, right? And it becomes you flip it right, and it becomes this one you flip it right, and then you apply the exponent. 1 times y over x to the 3rd power will just give you y to the x to the 3rd power, right? So you can go from here to here, guys. That's what I was mentioning earlier on some of the rules. That's why I went from here to here. If you have a negative exponent, all you do is flip it, and the exponent becomes positive. Okay. For example, here, by applying the rule, right, we can use a reciprocal, right, of 2/5 and make it positive. Now this becomes 5 squared divided by 2 squared, which will give us 25 over 4. So this is my result. Now comes rule number 7. I believe I gave you good examples, right, of how it can be. Okay, so I believe well, this was enough, but because I thought students should understand with 4 examples. Now for the zero property exponent, or for the zero exponent rule, anything to a 0 power will always be 1. Here I got a little bit sarcastic, right? So here I went to the extreme. If you have everything's to the parentheses, right? I mean, everything is inside the parentheses. That's why the rule applies. If you have parentheses x, y, z close parentheses to a 0 power, it's going to give us 1. So anything to a 0 power is 1. Now comes the fractional exponent rule. I believe this was rule number 8, I think. Yeah, rule number 8. This is crucial, guys, and I believe a lot of students have a hard time simplifying, going back and forth, going from exponential to radical and radical to exponential. So this is the rule that I mentioned earlier on the slide that had all the rules. Okay, so let's see how it works. Right, so the n is called my index, right, which will be my denominator right here on the exponent, on the power of on the exponent power, and then right, that's my n. A is called the radicand. It's also called the base. Here it's called the radicand, but in the exponential fraction is called the base. My m is my exponent, right? And that's also my numerator, right? Because we have m divided by n, a to the m divided by n, right? The n is your index and the m is your exponent. And this is called the radical symbol, right? That's called the radical symbol. So it's always good to know the vocabulary when you're using math. Okay, now, so again, a to the n divided by n, right, is equal to the nth root of a to the n power. And here's an example. They want you to write x to the 1/3 power into a radical expression. So here, the 3, right, the denominator is going to be your index, right? This is my index. And we have x, right? We don't have to put a 1 to the first power because anything, because this x to the first power is the same thing as just x. So number 26 here, x to the 1/3 power equals to the cube root of x. That's how you write it. Okay, now here, right? So the x is my radicand, my 5 is my index, right? From here, my 5 is my index, and the 3 is going to be my numerator. There's my answer, guys. You have to know how to go back and forth. Okay? If you notice here, the whole 3w, guys, right, is raised to the 2/3 power. That's why here's where a lot of students make a mistake. If it was like 3w to the 2/3 power, I mean, without the parentheses, only the w will be to the 2/3 power, not the 3. But in this case, this whole here expression, 3w is raised to the 2/3 power. That's why it's inside the parentheses, which means this whole thing will be this whole thing is a base, and it's also called my radicand. Okay, so this whole thing goes inside the radicand, and there's my index, which is the denominator here in the fraction, and here's my numerator, right, which is a 2 here as the exponent. Okay. Now they want you to go the other way, right? So again, right, the 8x to the y, 8xy, it will be like my a. So that's going to be my base, right? Then the n is my index, and my m is my exponent. So put it together. That's my a, right? That's my a to the power of 2 divided by 7. That's how you go from radical to exponential. Okay? There's here the same thing. My 6x is going to be my a, right? It's going to be my index. The 6x will be my a. The 4 is my index, which is a denominator. Since there's nothing there, right? Because this means if you have just 6x, it just means it's going to be raised to the first power, which is the same thing as 6x. So this is how you rewrite a radical into an exponential fraction. Here's what I tell you guys about the common mistake. If you have 6x to the 1/4 power, right? In this case, the 6 is not part of the exponent here, only the x. So please be careful. Well, you see, only the x is raised to the 1/4 power. So the 6 is in the outside because the x is like your base, right? And the base is a radicand. Here in the radical. And the denominator is your index. So this is how you, if it was in this form, this will be the answer. 6, the 4th root of x. So please be careful with those. Now, simplifying radicals. So to simplify radicals, you need to know basic roots such as square roots, cube roots, and 4th roots. And I believe I went over this today in class for the NCBN. Okay, so these are the square roots. The square root of 1 is equal to 1. The square root of 4 is 2. The square root of 9 is 3, right? And so forth. You must know all these, at least all the way to 100, right? And finally, the square root of 100 is equal to 10. And why are these perfect squares? Because if you notice, 1 times 1 will give you 1. 2 times 2 will give you 4. 3 times 3 will give you 9, and so forth. That's why these are called perfect squares, or square roots. So please try to memorize or try to understand or know 1 through 10, or from the square roots 1 to 100. Okay? These are the cube roots that you should know at least up to this point. The cube root of 1 is equal to 1. The cube root of 8 is 2. The cube root of 27 is 3. And the cube root of 64 is 4. And the cube root of 125 is 5. At least know all the way to 5 here. These are the fourth roots. The fourth root of 1 is 1. The fourth root of 16 is equal to 2. The fourth root of 81 is equal to 3. And I believe that's as far you should be able to know. At least know up to here, guys. At least. Okay? So example of simplifying a radical. Say you give 24. This is a square root, right? Because there's nothing there, so we know it's a square root. So is 24 here, guys? No, it's supposed to be here, right? So 24 is not a perfect square. Right? Is 24 a perfect square? No. So then let's find out factors of 24. How can I get 24? But let's go in order. 1 times 24, 2 times 12, 3 times 8, and 4 times 6. From here, guys, from all these factors, which one is the greatest per square? If you notice, it's going to be 4. Right? So it's going to be 4. So this is a combo that I'm going to use. So 24, the square root of 24 equals, right? Because this, so here comes, it's going to be the square root of 4 times the square root of 4 times 6. The square root of 4, right? You can separate them like this. You can go from here to here, right? Or I do it this way because from here you can apply the rule that you can break them apart, because when you multiply the square root of 4 times the square root of 6 will give you the same thing as the square root of 4 times 6, which will give you 24. So in other words, you can go from here to here. And why do I put the perfect square first? Because it's better when you write it down. You see, this will be 2 square root of 6. Because if you write it the way, the other way around, if you put square root of 6 times square root of 4, you can have square root of 4 times 2. And at times students might get mixed up and actually include the 2 as part of the radicand. That's why you always put the perfect square first. So the square root of 24 is equal to 2 times the square root of 6. Okay, so there's your solution. Now, I know that I should have given you more examples, guys, but this is only like a 50-minute, or an hour workshop, and I have to make sure that I cover everything. Okay, but you can ask the tutors if you need help afterwards, or you can ask me, and I can help you how to do more. Or maybe on my next PowerPoint that I do next semester, maybe I can add a few more. Now, examples of exponential functions. These are exponential functions. And I believe this is how 4.1 starts in the math 3024. Okay, exponential functions. And they start by doing examples of which ones are exponential functions. So all these are considered exponential functions. Why? Because the exponent is a variable. You see, notice? That's the exponent is a variable. Right? So recall a to the mn, right? Because you're going to be doing that, right? This is equal to this, when you graph, is going to be f of x equals to a to the x power, right? Mn is like my x, because we're going to be graphing now. The next thing that I'm going to show you guys is how to graph. But in the meantime, let's continue with this slide here. A is a base. The exponent is a variable, right? Which is a letter. Frequently is going to be x, but this can be also y. It can be whatever they want to put there in math. But most of the times they like to use x. Okay. So it's equal f of x equals to a to the x. And remember, the mn is like my x. This can be an exponent as a fraction, or it can just be a single whole number or integer. it has to be more than 0, right? For this to work, because now we're going to be evaluating, which leads to graphing. All this is to graph. Okay, how do we graph f of x equals to a base to a power of x? This is the most common exponential function to graph. So we're going to plug in x equals to -2, -1, 0, 1, 2, and 3. We always try to use these numbers when we're graphing. Okay, so how do we evaluate the function at these values for x? Okay, so let's do a table, right? The f of x is like my y. So I'm doing my table here, right? There's my -2. Here we go. So f of x equals to 2 to the x power. So when x is -2, right, I'm going to plug in -2 where the x is, right? I'm going to plug it in there, right? By applying the negative exponent rule, right? This becomes positive, but it's going to be 1 over the base to the exponent being positive now. So this becomes 1/4. So when x is -2, y is 1/4. When x is -1, right, we go back here. So we're going to evaluate at f of -1. So we're going to plug in -1 where the x is as the exponent. So 2 to the -1 is going to give us 1 over 2 to the first power, which simplifies to 1/2. So when x is -1, y is 1/2. There it is. Now let's try 0. So let's evaluate f of 0, right? So when x is 0, we apply the property, right, that anything to a 0 power is always equal to 1. So when x is 0, y is 1. Now let's use 1. Let's evaluate at x equals 1. So let's find f of 1. So when we find f of 1, right, so we evaluate f of 1, we're going to plug in 1 right there where the x is, right? That's why there's my exponent, which is 1. So 2 to the first power is equal to 2. So when x is 1, y is 2. Now let's evaluate at f of 2. Right, so we keep repeating the procedure, but just adding these all values for x, which that was given, right? And we put a table. So f of 2 is equal to 2 to the second power, which is equal to 4. So when x is 2, y is 4. And lastly, when x is 3, right, we're going to evaluate f of 3, which means I'm going to plug in 3 for the x's as an exponent. So 2 to the third power is equal to 8. Why 8? Because 2 times 2 times 2, 3 times, right, is equal to 8. So when x is 3, y is 8. Now, let's graph it. So here it goes, right? So this is like the parent graph, guys. You see, this graph, everything has to do exponential, will always start low and it begins increasing as the numbers get bigger for x. And if it's if the base is if the exponent is between 0 and 1, then it's going to be the other way, which I'm going to be graphing the next one on the next slide. But if you notice, guys, when x is -2, right, it's right here, -2, y is 1/4, which means you're going to cut this this unit here, a 1, into 4 places. So I'll be like 1, 2, 3, 4, right? So 1/4 will be about right there. And then when x is -1, right, -1 is going to be about 1/2. And then when x is 0, right, when x is 0 is going to be 1. Then when x is 2, when x is 1, right, it's going to be 2. So it's going to read, see, right, there's 2. And when x is 2, it's going to be 4. So you keep plotting your points. And when it's 3, it's going to be 8, right? So then all you do is I'll connect the points, and that's your graph. If you notice, these are the points that are most commonly used, because if you use 4, 2 to the fourth power is going to give us 16, right? And 16 will be up here on the top, right? It's going to be out of range. That's why be wise on the points that you use, for the x value. And these points will always work best. Okay. Now, continue. Right, so this is like the parent, right? If you have a base to the x power, and if a is more than 1, right, it's going to be exponential growth, which means it's low, and as x increases, as x gets bigger, so does y get bigger. This is called the graph characteristics. The graph is above the x-axis, right? The graph, this is my x-axis, the graph is above the x-axis. The y-intercept will always be 1. The graph climbs steeply to the right, right? It goes to the right, steeply. The negative x-axis is the horizontal asymptotes. You see, this graph will never touch the x-axis. As it goes down to the negative, it will get closer and closer to 0, but it will never touch the x-axis. The larger the base A, the more steeply the graph rises to the right. So, for example, say this was a 2, right? So the 2 will be like the one that we just graphed. If there was a 3, the graph will be going something like this, steeper to the right. If that was a 10 to the x power, the graph will probably be something like this, real close to the y. So the bigger the base, right, the more it goes towards the y-axis, or the steeper it gets. Okay, so these are my graphs, right? For example, this is y to the 2x, right? It's in green. And then if you have y to the 3, y to the 3x, right? So this is right. It gets bigger. So it keeps getting closer and closer to the y-axis. It gets steeper. You see, this is 1.5, right? So if it's between 1 and 2, right? Say not 1, but say between 1 and 2, the graph will be open like that, closer to the x-axis. So the bigger the base, the more the graph goes towards the y-axis. That's what it means there. Okay. Now let's see when A is between 0 and 1. This is called a decay, exponential decay. And here are the graph characteristics. The graph is above the x-axis, right? It's above the x-axis. The y-intercept is 1 again. The graph falls sharply to the right, right? It goes from high and it falls to the right. The positive x-axis is the horizontal asymptotes, the same as the one before, right? The graph will never touch my x-asymptotes here, the x-axis. And the smaller the base A, the more steeply the graph falls to the right. Okay? So the smaller the A, the more the graph goes to the right. Just like the one here, right? The bigger it was, the higher the A, the more it went here towards the x-axis. To the y-axis. Okay, now let's see here. And here's my graph for that one. You see? So this is what the 1/2, right? Then this is 1/3. So the smaller the smaller the base, the more it goes to the right. And the bigger the base, the more it goes towards the x-axis. Now, exponential functions, graphs continues. So let's graph this one here. Okay, right? By applying the rule, right? Isn't this the same thing as 1/2 to the x power? This is the same thing as 1/2 to the x power, because x to the first power, 1 to the x power will always be 1, because 1 to any power will always be 1. That's why this is equivalent to parentheses 1/2 close parentheses to the x power. Now this time we get the graph, right? We're going to plug in the exponential for x, -3 all the way to 3. So if you notice, right, I'm going to plug in 3 here for the x. So we're going to evaluate g of -3, right, which would be 1/2 to the -3rd power. Remember the rule that I showed you earlier, right? If you have a fraction raised to a negative power, right, you flip the fraction, right, reciprocal, and it becomes positive. So that's equals to 8, right? So the 8 goes there. And you repeat the process for all these values here, right? For all these values here, you repeat the process. And just plug them in there, guys. And that's why these are the answers here. So that's my graph for 2 to a negative x, which is equal to 1/2 to the x power. And in the same graph as before. Okay. Now logarithms. Until the development of computers and calculators, logarithms were the only effective tool for large-scale numerical computations, no longer needed for this purpose because now we have calculators. Definition of logarithms to the common base 10. Y equals to log of base 10 to the x, right, is the same thing as y equals to log of x, because if there's no base, it's base 10. And this is logarithmic, this is exponential. So this is equal to this right here. For example, y equals to log base 10 to the x means 10 to the y equals x. No base, right? It's base 10. Simplifying without a calculator. Right? These two are the same, right? Log and no base is base 10. This is how you read it. To what exponent must 10 be raised to get x? Okay. For example, here, by applying what I just mentioned, to what power the exponent must be raised to get x? To what power, right? Must 10 be raised to get 100? That's how you read this here. So it's going to be, right, 2, because 10 squared will give me 100. This one here, to what power, right? Well, can I raise 10? To what power? That give me, 10,000. So it's going to be 1, 2, 3, it's going to be 4, right? Because 10 to the fourth power is equal to 10,000. Okay, how about this one here? To what power should we raise 7 to give me 49? The answer is 2, because 7 squared is equal to 49. This one here, to what power should we raise 3 to give me 27? Right, so the answer is going to be 3. And later on, I'm going to show you how to solve these, which I think is going to be next week. Write exponential equations into logarithmic equations and vice versa. Here's my definition. Definition of logarithmic to a base 8. If you have y equals to log a base 8 to the x, means 8 to the y equals x. So this is in logarithmic form, which is equivalent to 8 to the y equals x in exponential form. Okay, so here they're going to want you to write each logarithmic equation into an exponential equation. So how should we do that? They give you log of base 981 equals 2. Right, so check this out. Right, so this is logarithmic form. We want it in exponential form. So you need to know what the a, x, and y is. Right, so my a is 9. Right, my x is 81. My y is 2. Now we put it in exponential form. So my a, right, is 9. My y is 2. And my x is 81. That's how you go from logarithmic to exponential. Write each exponential equation into logarithmic form. Now they're going to go the other way, right? Then, right, we put the exponential form here. So my a, right, so we want it from exponential to logarithmic now. So I need to know what the a, x, and y is. So my a is 5. My y, right, is 3. My x is 125. So what's my y? My y is 3. Right? My a is 5, right there. And my x is 125. Or you can put it the other way around. Log of base 5 of 125 equals 3. So these two is the same thing. Now, logarithmic function graphs. In order to graph without a calculator, must convert logarithmic equation into an exponential equation. That's why it's important to go from logarithmic to exponential, right? So this is my logarithmic form. This is my exponential form. So right, so this is equal to, right, 2 to the y equals x. So this graph 2 to the y equals x, but instead of putting the values for x, we're going to put in for y. Because it's going to be kind of complicated if we put the values for x, which it can be done, but you guys do not know how to do it yet, okay? But this can be done. They're going to explain to you that when you solve for logarithmic equations and stuff like that, you're going to be able to understand how to do it. But for now, this has not been explained yet, so that's why it's easier to plug in the values for y instead of x, right? So if we repeat the process from before, right? If we put here -2, it's going to give us 1/4. That's where the 1/4 came from. If we put -1, right, for the y, 2 to a -1 will give us 1/2. Right? So all these are the answers as before. Because before we plug them into the x values, right? And this is what we got for the y values. So in other words, this is my exponential in blue, and this is my logarithmic equation in red. These are inverse of each other, okay? So for now, guys, let me go back real quick. So for now, guys, I know that I barely covered the graphs because I wanted to make sure that I went kind of slow for you guys to understand to try to understand the material, and also so we can have practice with the tutors where you can ask me questions. Right now because we're done. I'm done with this PowerPoint or with this presentation. Okay, let me go back. Let me stop sharing my screen.
At this time, is there any questions for Mr. Azasi? All right, well, if there's no further questions, I'm going to go ahead and I'll move on. We're going to talk about what's going to happen in this for Happy Math Hour next week. So for 1 o'clock, for the Academic Success Series, we're going to have EPCC Mental Health Committee on Staying Strong, presented by the wonderful Mr. Christian Salas. And then for Happy Math Hour, for Math 1314, we're going to be covering synthetic division and complex numbers. And for Math 1324, hosted by our very own Mr. Azasi, we'll be solving exponential and logarithmic equations. I want to thank you all for coming today. Thank you, as always, Mr. Azasi, for doing an awesome job. And I hope you all have a wonderful weekend.